Hello everyone. Today is our last lecture before the final exam. Okay, so our major task today will be review the early chapters. So our review will only focus on chapters 1 to chapter 5. Okay, this is covered by the first and second midterm exams. I assume that your memories are still fresh for the second half of the semester, so we only focus on the first 5 chapters. But before everything, let's emphasize the schedule of a final exam. As shown in this schedule, you will see that our classes here, CE 2210, the final exam schedule is here. So next Wednesday, 12:30 to 2:30 p.m. Okay, so our final exam will be held at the same as scheduled here. So the form will be very much similar to the exam 3 and exam 4. I'm not sure how many multiple choices will be, and how many non-multiple choice problems will be. Since yesterday, that was the first time we encounter non-multiple choice question. Okay, this might be a form, so we will have a discussion later to see if we will include more non-multiple choice problems in the final exam. Okay, so normally in a final exam, we only allow students to take a 4-page formula sheet that we used in exam 1, exam 2. But since you are taking the final exam at home, so we have no way and we have no reason to restrict the materials you use. I think you can use everything you want, but you will have a time limit, right? It's 2 hours. You can use the 4-page formula sheet since most of the equations have been summarized on the sheet, but not all. Okay, so sometimes you need to use some equation to calculate a parameter, a constant, but you will not be able to find the equations from the formula sheet. In that case, you should be familiar with your notes, with your slides, and be familiar where to find these equations. I will give you several examples. For example, sometimes we have hollow circular shaped cross section, right? So you will need to use the I to calculate something, right? So how to calculate the I for this shape? If you have been familiar with the equations, you can easily write that this equals pi over 64 d to the fourth minus d to the fourth, right? This is the equation. But if you forget it, so you need to know where to find out this equation. It's not available on the formula sheet. Okay, you can, as I suggested, you can summarize your own formula sheet. Right, it's review the formula sheet to see what equations are not available on it, and then make up them. So this is the first example. Then also for this hollow circular shaped cross section, you may be able to, no, you may need to find the Qmax, right? The Qmax of this case. How to calculate it? Let's go to our chapter. So which chapter? In the shear, right? The shear flow part, right? Just go there to find out the equation. Okay, just when you need to determine the Qmax of this cross section, you need to use the equation, but this equation is not available on the formula sheet. Another example that's not available on the formula sheet is that if you want to calculate the longitudinal strain in a non-spherical pressure vessel, okay, the equation should be PD over 4TE times 1 minus 2 Poisson ratio. Okay, so this is the equation, but you cannot find it on the formula sheet. You need to find it out from your notes, from your slides. Okay, so speaking Poisson ratio, okay, we were tested yesterday. It's a discussion, right, regarding if those test results are valid and how to calculate the correct Poisson ratio, etc. Okay, I will make a video later to go through more details about that question. This is very important. Okay, I found that many of you were not clear about the concept of the Poisson ratio. So I think it's necessary to emphasize this concept and give you more details and more hints to correctly answer some questions related to Poisson ratio. Okay, so then let's start to review these first 5 chapters. So in our chapter 1, I hope you still remember what did we learn from chapter 1. Okay, the title side is stress and strain. Right, this is chapter 1. And we introduced 3 types of stresses and 2 types of strains. Right? So for stress, we had 3 types of stresses. The first one is called normal stress. How to calculate normal stress? Just sigma equals F over A, right? The axial loading over the cross-section area. In later chapters, we learned some other methods to calculate normal stress, but in chapter 1, this is the only equation, right? Oh, the second one is shear stress. For shear stress, the equation is just tau equals V over A, the shear force over the cross-section area. Right? And what is the third type of stress? It's called bearing stress, right? So what is the nature of a bearing stress? Is that a normal or shear? Right, so it's a normal, right? It's due to compression. So it's just a bearing stress equals something. Okay, a simplest case is that you have a steel plate and you have a hole on it. Then you have a bolt to connect it to some other structural components. So the load is applied to this bolt. We have F here. So you have a kind of stress generated on the interface between the 2 components. Right? So theoretically, you need to use a force over the area, but the area of the interface is not easy to calculate. So to simplify that, is we will only need to thinking about this projected area. Okay, so you just use a projected area to calculate the effective bearing stress. Right? So theoretically, strictly speaking, at different points on the interface, you have different stress values and even directions. Right? But here we do not think about in that scientific ways. We just thinking about it in the engineering way. Right? We simplify it and only consider the projected area to calculate the effective bearing stress. The equation is very simple. It's just F over the projected area. You just go back to figure out how to determine the projected area. Okay. And for strain, we have 2 types of strains. It is a normal strain and shear strain. Well, the normal strain can be calculated by a simple equation that is epsilon equals delta over L. Right, the delta is the length change, and the L is original length, right? So that is just a simple case is that you have a bar. So when you load it, it become longer. Right, so this is delta, and here is L. Okay, when you add F to it. Okay, so this is our delta over L is the normal strain. And the unit, what's the unit of a strain, normal strain? It's unitless, right? Unitless, but normally we use micro strain to denote the unit, but it's actually unitless. So what is the positive and what is the negative? So in this case, in this example given, this become longer will be positive, right? Become shorter will be negative, right? So this is easy to understand. Then how about the shear strain? Or shear strain can be calculated by this equation. This gamma equals delta x over L. What's the unit? Unit is kind of microradian. Since this is the angle, right? So the nature of the shear strain is the angle. Okay, we can also give an example. This is x direction, y direction, and this is the original shape of it. The original shape of an element. And it's subjected to shear. Right after this shear tau is this shear force is added, so it will deform. Deform to this. Okay. After the deformation, you get here. This is the gamma. Okay, this angle is the gamma. So the original. Okay, so here is delta x, and this is L, right? So using these numbers here, you can calculate the gamma, that is delta x over L. So this equation is only valid when this deformation, when this gamma is very small, right? When it's large, you cannot use this equation. You need to use a inverse tangent, right? Use inverse tangent to determine the gamma. But when this angle is small, it doesn't matter, since gamma will equal sine gamma equal tangent gamma when the angle is small. Right? More important thing is that the positive and negative. So what is the positive gamma? What is the negative gamma? Assume that in the beginning, the angle between x and y is 90 degrees. If after deformation, this angle between x and y becomes smaller than 90 degrees, is that positive or negative? That would be positive, okay? When the angle between x and y becomes larger than 90 degrees, it will be what? Negative, okay? So when the angle becomes larger, it will be positive. When it becomes smaller, it will be it's when this angle becomes smaller, okay, it will be positive. That is, when the xy becomes smaller, the angle between x and y becomes smaller than 90 degrees, it will be a positive shear strain. But if it's larger than 90 degrees, This is X, that is Y. Then it will be negative shear strain. And in chapter 2, the mechanical properties and design concept, right? Mechanical properties and design concept. So we had 3 parts in this chapter. The first part, we just introduced the Hooke's law. Okay, the correlations between stress and strain. Okay, the Hooke's law has a series of equations, and for the 1D compression or tension, you have stress equals E times strain. So the modulus of elasticity can be defined as sigma over epsilon. Right? So in the same way, when the 2D element is subjected to shear, so the tau equals G times gamma. Right? So the G will be calculated by tau over gamma. Okay, this is the Hooke's law. Right. And another important parameter here you need to know is that it's the Poisson ratio. Right? Okay, the Poisson ratio is negative latitude strain over longitudinal strain. Okay. So here comes a question. Since many students made that mistake yesterday in the discussion problem. Okay, here is the first question for Poisson ratio. Is the Poisson ratio for a normal material positive or negative number? In the slides, you saw that our Poisson ratio is normally 0 to 0.5 for normal engineering materials, right? So the upper limit 0.499 is for rubber. Right? So other normal engineering materials like steel, concrete, their Poisson ratios are just between 0 and 0.5. Okay, for concrete, it's normally 0.2 to 0.3, something like that, or 0.33. That is a normal range of a hard engineering material. Right? But it's a positive number, right? Why? Just look at the definition of Poisson ratio. This equation, right? It equals negative ratio between these two. But look at this too. The longitudinal strain and latitude strain. Consider a bar or plate. When you stretch it along one direction, so what will happen along perpendicular directions? When you stretch it along one direction, along the perpendicular directions, it will tend to shrink, right? So in one dimension, it will become longer, positive, right? In other directions, it will become shorter or negative. Okay? When you compress components, it will become shorter along this direction, but along the perpendicular directions, it will tend to expand. So these two strains will always have opposite signs. So this Poisson ratio is normally a positive number, okay? Because these two, they have opposite signs. Okay, I remember one student asked me, is that possible that a material has negative Poisson ratio? The answer is yes. Okay, but that is not normal engineering materials. You can Google negative Poisson ratio materials. You will be able to find something. Okay, if you are interested, just go search it. But for engineering, like in civil engineering, mechanical engineering, in the regular engineering practices, the materials are all positive Poisson ratio materials. Okay, another equation is also important. The equation is used to correlate these three components, these three constant. Okay, this is G equals E over 2 times 1 plus nu. Okay, so this is an important equation to correlate the three mechanical constant. Okay, in the second part of chapter 2, we talked about thermal expansion. Okay. So the core equations are the strain due to thermal expansion equals alpha times delta T, and alpha is the coefficient of thermal expansion. Right? If you want to determine the length change due to temperature change, this delta T, you can just use the strain times original length, right? Or alpha delta T original length. Okay, so those are the two equations we use, basic equations we use to calculate thermal expansion related problems. We used this concept to design fancy thermometers. Okay, we had a couple of examples to design different types of fancy thermometers. Okay, the basic one is that you have a wall and you have a mirror, and you connect your mirror to the wall using two bars with different alpha, with different coefficient of thermal expansion. Okay. So you can heat it, assuming that the temperature in the environment becomes higher. So you are heating these two bars. So the first bar will become longer, and the second bar will also become longer. But because the coefficient of thermal expansion of the second bar is larger, so its elongation will be larger. So as a result, the mirror will be inclined. Right? So assume that you have a laser here. So the laser is injecting the mirror from this angle. So it will be reflected to here. Okay. So if you measure the distance A, so you'll be able to use this A and the alpha of the two different bars to calculate the temperature change. Right? It's correlated the A to temperature change. So you can use this mechanism to design and to produce a thermometer, right, to monitor the temperature change in the environment. Another set of classical questions is that can thermal expansion lead to stress? Can thermal expansion lead to stress? Okay, so what's your answer? Can thermal expansion lead to stress? Notice, consider a bar, okay? A free bar. Just put it there and you heat it. It will expand, right? So do you think any stress will be generated in it? So if you ignore the heterogeneous distribution of temperature in this thin bar, so you can say that so no stress will be generated in it. But strictly speaking, there will be something, but we ignore that if you consider it as a thin bar. Okay, when you fix one end, so this bar will still be able to deform freely, so no stress will be generated. The case is, how about if you fix two ends of a bar? Okay. If a bar fixed to end of it, then you hit it, what will happen? It will tend to expand, but the expansion is not allowed, right? Since two ends have been fixed, has been clamped. So it will tend to expand but not allowed. So it's equivalent to a case that you allow its expansion, then push it back to the original length, right? So as a result, a compressive stress will be generated in it. But if you cool it, then it will tend to shrink, but you do not allow it to shrink, you stretch it back, right? So as a result, a tensile stress will be generated in it. Right? So those are the cases. And go back to review our examples. And in part 3, so are just the design problems, the basic design problems. And our core concept in here is the allowable stress equals the strength, yield stress or strength of the material over factor of safety. Okay. So here, using this basic equation, we can request you to do different types of calculations. In the first step, you may need to determine the maximum load. The maximum load allowed based on strength and factor of safety. Right. The second type, you may be requested to design the dimensions based on desired loading, strength of material, and factor of safety. Of course, sometimes you will be given the strength and loading, etc. So you just need to calculate the factor of safety in the structure, in the existing structure. So those are the possibilities of using the basic design equation. Okay, so those are the concepts and equations in the first 2 chapters.